The number of motors that can be installed in an underground duct bank is limited by the cable ampacity and conduit fill capacity. The ampacity of a cable is the maximum current it can carry without overheating. The ampacity is affected by several factors, including cable size, conductor material, insulation type, ambient temperature, and conduit fill. The conduit fill capacity is the maximum percentage of the conduit cross-sectional area that can be occupied by cables. The conduit fill is limited by NEC requirements, usually 40% for underground feeder cables, cable bending radius, and heat dissipation. In general, the number of cables that can be installed in a duct bank is determined by the largest cable diameter and the conduit fill capacity. However, for multiple cables in a duct bank, there is a derating factor that must be applied to the cable ampacity. The NEC requires that the ampacity of multiple cables in a conduit be multiplied by a derating factor. For 2 to 3 cables, the derating factor is 0.8. For 4 to 6 cables, the derating factor is 0.7. For 7 to 9 cables, the derating factor is 0.6. For 10 or more cables, the derating factor is 0.5. The NEC National Electrical Code provides specific requirements for the installation of cables in underground duct banks. Article 310.10 states the ampacity of a conductor shall not exceed that for which the conductor or cable is approved. Article 300.5 states conduits shall not be filled to more than 40% of their cross-sectional area. Article 310.15b3 states the ampacity of a conductor installed in a conduit shall be adjusted based on the derating factors provided in Table 310.15b3a. There are some exceptions to the NEC requirements for conduit fill and derating factors. These exceptions include underground service conductors. The ampacity of service conductors in underground raceways can be adjusted by multiplying by the following factors. For 2 or more conductors, the derating factor is 0.7. Conductors in parallel means the ampacity of conductors in parallel can be adjusted by adding the ampacities of the individual conductors. As a practical example, with motors ranging from 1 horsepower to 250 horsepower and duct bank runs of up to 400 feet, it is likely that you will need to derate the cable ampacity. Assuming you are using underground feeder cables, 40% conduit fill capacity, the derating factor for 15 motors would be for a 200-foot duct bank, 0.8 for 2 to 3 cables. For a 400-foot duct bank, 0.6 for 7 to 9 cables. This means that the cable ampacity for 15 motors would be reduced by 20% to 34%. To accommodate 70 motors in an underground duct bank, you will need to consider the following options. Firstly, increase the duct bank size by installing a larger duct bank to accommodate the increased number of cables. Secondly, use larger cables by installing larger cables to increase the ampacity. Thirdly, reduce the number of motors by considering reducing the number of motors in each duct bank. And fourthly, consider exceptions by exploring if any of the exceptions to the NEC requirements can be applied to your situation. The number of motors that can be installed in an underground duct bank is limited by the cable ampacity and conduit fill capacity. The NEC provides specific requirements and derating factors for multiple cables in a conduit. It is important to follow these requirements to ensure the safe and reliable operation of the electrical system. The electrical systems rely on conductors to safely and efficiently carry electrical current to various loads. The ampacity of a conductor, which is the maximum current it can carry continuously without exceeding its temperature rating, is a critical parameter. Understanding and correctly applying ampacity principles is essential for ensuring the safe and reliable operation of electrical installations. Conductor ampacity is primarily determined by the conductor material, size, and insulation type. Copper and aluminum are the most common conductor materials, with copper generally having a higher ampacity for a given size due to its lower resistivity. The size of the conductor, typically expressed in American wire gauge, directly affects its ampacity. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. The insulation type also plays a significant role in determining ampacity, as different insulation materials have different temperature ratings. Common insulation types include THHN, THW, and XHHW, each with specific temperature and environmental characteristics. The National Electrical Code provides detailed ampacity tables, such as NEC Table 310.15b16, which lists the allowable ampacities for various conductor types and sizes under specific conditions. These tables are based on an ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit, and no more than 3 current-carrying conductors in a raceway or cable. However, real-world installations often deviate from these standard conditions, necessitating the application of correction and derating factors. Ambient temperature correction is necessary when the actual ambient temperature differs from the 30 degrees Celsius reference temperature. Higher ambient temperatures reduce the conductor's ability to dissipate heat, thereby lowering its ampacity. Correction factors are applied to the ampacity values in NEC Table 310.15b16 to account for these temperature variations. For example, if the ambient temperature is higher than 30 degrees Celsius, the ampacity must be reduced by multiplying it by the appropriate correction factor from NEC Table 310.15b2. The number of current-carrying conductors in a raceway or cable also affects ampacity. When multiple conductors are bundled together, the heat dissipation is reduced, leading to a decrease in ampacity. NEC Table 310.15b3 provides derating factors for various numbers of current-carrying conductors. For instance, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. For 7 to 9 conductors, the derating factor is 70%, and so on. These derating factors are cumulative, meaning that if both ambient temperature correction and conductor bundling derating apply, both factors must be considered. Voltage drop is another critical factor in conductor selection. As current flows through a conductor, it experiences a voltage drop due to the conductor's resistance. Excessive voltage drop can lead to reduced equipment performance, overheating, and potential equipment failure. The NEC recommends limiting voltage drop to no more than 5% for feeders and 3% for branch circuits. To calculate voltage drop, the following formula can be used: voltage drop equals current times resistance times length, divided by 1000, where current is the current in amps, resistance is the conductor resistance in ohms per 1000 feet, and length is the one-way conductor length in feet. Selecting a larger conductor size can reduce voltage drop, but this must be balanced against the increased cost of the larger conductor. Conductor sizing also depends on the specific application and type of load being served. For motor circuits, the NEC requires that the conductor ampacity be at least 125% of the motor's full load current. This is to account for the motor's starting current, which can be significantly higher than its running current. For continuous loads, which are loads that operate for 3 hours or more, the conductor ampacity must be at least 125% of the continuous load current. This requirement ensures that the conductor can handle the sustained heat generated by continuous operation. Overcurrent protection devices, such as circuit breakers and fuses, are essential for protecting conductors from overloads and short circuits. The overcurrent protection device must be sized to protect the conductor based on its ampacity. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the conductor size and type. The overcurrent protection device should not exceed the conductor's ampacity unless specifically permitted by the NEC. For example, small conductors, such as 14 American wire gauge and 12 American wire gauge, have specific overcurrent protection limits to prevent overheating. In addition to ampacity, other considerations in conductor selection include the environmental conditions and installation methods. Conductors installed in wet locations or exposed to corrosive substances must be suitable for those environments. Threat burial cables must be specifically designed for underground installation and must be protected from physical damage. The installation method, such as in a raceway cable tray or free air, also affects the conductor's ampacity and must be considered during conductor selection. Proper conductor termination is crucial for ensuring a reliable electrical connection. Conductors must be properly stripped, cleaned, and terminated using appropriate connectors. The connectors must be compatible with the conductor material and size, and they must be taught to the manufacturer's specifications. Loose or improperly terminated connections can lead to overheating, voltage drop, and potential fire hazards. Regular inspection and maintenance of conductors and their connections are essential for preventing electrical problems. Conductors should be visually inspected for signs of damage, overheating, or corrosion. Connections should be checked for tightness and integrity. Any damaged or deteriorated conductors or connections should be replaced immediately to prevent electrical hazards. Understanding and applying ampacity principles correctly is crucial for ensuring the safe and reliable operation of electrical installations. By considering factors such as conductor material, size, insulation type, ambient temperature, conductor bundling, voltage drop, and overcurrent protection, electrical professionals can select the appropriate conductors for each application and ensure the long-term performance of electrical systems. In the context of underground duct banks, the principles of cable ampacity and conduit fill become even more critical due to the confined environment and potential for increased heat buildup. An underground duct bank is a system of conduits or raceways installed underground to carry electrical cables. These duct banks are commonly used in commercial, industrial, and utility applications to distribute power and communications signals. The design and installation of underground duct banks must adhere to specific codes and standards to ensure safety and reliability. The number of cables that can be installed in an underground duct bank is limited by the cable ampacity and conduit fill capacity. The cable ampacity is the maximum current a cable can carry continuously without exceeding its temperature rating, while the conduit fill capacity is the maximum percentage of the conduit's cross-sectional area that can be occupied by cables. The NEC provides specific requirements for conduit fill, typically limiting it to 40% for most applications. This limitation is intended to provide adequate space for heat dissipation and to prevent physical damage to the cables. The ampacity of cables in an underground duct bank is affected by several factors, including cable size, conductor material, insulation type, ambient temperature, and the number of cables in the duct bank. The NEC provides ampacity tables that list the allowable ampacities for various cable types and sizes under specific conditions. However, these ampacity values must be adjusted based on the actual conditions of the installation, including ambient temperature and the number of cables in the duct bank. When multiple cables are installed in a duct bank, the heat dissipation is reduced, leading to a decrease in ampacity. The NEC requires that the ampacity of multiple cables in a conduit or duct bank be derated based on the number of current-carrying conductors. The derating factors are specified in NEC Table 310.15b3 and vary depending on the number of conductors. For example, if there are 4 to 6 current-carrying conductors in a duct bank, the ampacity must be derated to 80% of its original value. For 7 to 9 conductors, the derating factor is 70%, and so on. In addition to derating for the number of conductors, the ampacity must also be adjusted for ambient temperature. Underground duct banks are typically installed in locations where the ambient temperature is higher than the reference temperature used in the NEC ampacity tables. Higher ambient temperatures reduce the cable's ability to dissipate heat, thereby lowering its ampacity. The NEC provides correction factors in Table 310.15b2 that must be applied to the ampacity values to account for ambient temperature variations. The design of an underground duct bank must consider the cumulative effects of conductor derating and ambient temperature correction. The allowable ampacity of the cables in the duct bank must be sufficient to carry the intended load, even after applying all applicable derating and correction factors. If the calculated ampacity is insufficient, the designer must either increase the cable size, reduce the number of cables in the duct bank, or improve the heat dissipation characteristics of the duct bank. The size and configuration of the duct bank also affect its heat dissipation capabilities. Larger duct banks with more space between conduits tend to dissipate heat more effectively than smaller, more tightly packed duct banks. The depth of the duct bank below the ground surface also affects its temperature. Deeper duct banks tend to have lower temperatures due to the greater thermal mass of the surrounding soil. The material used for the conduits in the duct bank can also affect its heat dissipation characteristics. Conduits made of thermally conductive materials, such as concrete or metal, tend to dissipate heat more effectively than conduits made of non-conductive materials, such as plastic. The NEC provides specific requirements for the installation of cables in underground duct banks. These requirements cover topics such as conduit fill, cable ampacity, conductor derating, and overcurrent protection. Adhering to these requirements is essential for ensuring the safe and reliable operation of the duct bank. In addition to the NEC requirements, local codes and standards may also apply to underground duct bank installations. These local requirements may vary depending on the jurisdiction and should be carefully reviewed before beginning any duct bank project. Proper installation practices are crucial for the long-term performance of an underground duct bank. The conduits must be properly aligned and supported to prevent physical damage to the cables. The cables must be carefully pulled into the conduits to avoid damaging the insulation. The duct bank must be backfilled with appropriate materials to provide adequate support and protection for the conduits and cables. Regular inspection and maintenance are essential for ensuring the continued reliability of an underground duct bank. The duct bank should be inspected periodically for signs of damage, such as cracks or settlement. The cable should be inspected for signs of overheating or insulation damage. Any damaged or deteriorated component should be repaired or replaced promptly to prevent electrical hazards. Understanding and applying the principles of cable ampacity and conduit fill is crucial for the safe and reliable design and installation of underground duct banks. By considering factors such as cable size, conductor material, insulation type, ambient temperature, conductor derating, and installation practices, electrical professionals can ensure that underground duct banks provide long-term performance and safety. In this specific scenario involving the installation of underground cables from a motor control center room to motors in the field, several factors must be carefully considered to ensure compliance with NEC and to provide a safe and reliable electrical system. The installation involves approximately 70 motors, ranging in size from 1 horsepower to 250 horsepower, and the motor control center room feeds motors in 2 separate buildings. The longest motor run in the first building is approximately 200 feet, while the conduit run in the second building passes through the first building and extends an additional 200 feet for a total of 400 feet. All the motors operate at 480 volts. The challenge lies in the engineering team's assertion that only 15 motors can be installed in each underground duct bank before significant derating is required, necessitating multiple duct banks spaced 5 feet apart. This configuration presents practical difficulties and raises questions about potential exceptions or alternative solutions. The number of motors that can be installed in each duct bank is primarily limited by the cable ampacity and conduit fill capacity, as previously discussed. However, the specific requirements and derating factors depend on the cable type, size, insulation, ambient temperature, and installation method. To determine the allowable number of motors per duct bank, a detailed analysis of the load requirements, cable characteristics, and environmental conditions is necessary. Firstly, the full load current for each motor must be determined based on its horsepower rating and voltage. The NEC provides tables, such as NEC Table 430.250, that list the full load currents for various motor sizes and voltages. The total load current for each duct bank can then be calculated by summing the full load currents of all the motors served by the duct bank. Secondly, the appropriate cable type and size must be selected based on the total load current and the applicable NEC requirements. The cable must have sufficient ampacity to carry the total load current, taking into account any applicable derating factors. The cable insulation must be suitable for the environmental conditions, including temperature and moisture. Thirdly, the conduit size must be selected based on the cable size and the NEC conduit fill requirements. The NEC limits the conduit fill to 40% of the conduit's cross-sectional area for most applications. The conduit must be large enough to accommodate all the cables without exceeding the fill limit. Fourthly, the ampacity of the cables must be derated based on the number of current-carrying conductors in the duct bank and the ambient temperature. The NEC provides derating factors in Table 310.15b3 for various numbers of conductors. The ampacity must also be adjusted for ambient temperature variations using the correction factors in Table 310.15b2. Fifthly, voltage drop must be calculated to ensure that the voltage of the motors remains within acceptable limits. The NEC recommends limiting voltage drop to no more than 5% for feeders and 3% for branch circuits. If the calculated voltage drop exceeds these limits, the cable size must be increased to reduce the voltage drop. Sixthly, overcurrent protection devices must be selected to protect the cables from overloads and short circuits. The overcurrent protection device must be sized to protect the cable based on its ampacity and the applicable NEC requirements. The overcurrent protection device should not exceed the cable's ampacity unless specifically permitted by the NEC. In a specific scenario, the engineering team's assertion that only 15 motors can be installed in each duct bank before significant derating is required should be carefully evaluated based on the above analysis. It is possible that the engineering team has made conservative assumptions about cable ampacity, ambient temperature, or other factors. It is also possible that they have overlooked potential exceptions or alternative solutions that could allow for more motors per duct bank. One potential exception is the use of parallel conductors. The NEC allows conductors to be run in parallel under certain conditions, which can increase the overall ampacity of the circuit. If parallel conductors are used, the ampacity of each conductor can be added together to determine the total ampacity of the circuit. This can allow for more motors to be served by a single duct bank. Another potential solution is to use cables with higher temperature ratings. Cables with higher temperature ratings have higher ampacities, which can reduce the need for derating. However, the equipment connected to these cables must also be rated for the higher temperatures. It may also be possible to improve the heat dissipation characteristics of the duct bank. This can be achieved by increasing the size of the duct bank, using thermally conductive conduit materials, or providing ventilation to the duct bank. By improving the heat dissipation, the ampacity of the cables can be increased, allowing for more motors per duct bank. The question of what constitutes a duct bank, whether it is 2 conduits or 10, is not explicitly defined in the NEC. However, a duct bank is generally considered to be a group of conduits that are installed together and carry multiple cables. The NEC requirements for conductor derating apply to any group of conduits that are installed together, regardless of the number of conduits. In summary, the installation of underground cables from a motor control center room to motors in the field requires careful consideration of cable ampacity, conduit fill, derating factors, voltage drop, and overcurrent protection. The engineering team's assertion that only 15 motors can be installed in each duct bank should be carefully evaluated based on a detailed analysis of the load requirements, cable characteristics, and environmental conditions. Potential exceptions and alternative solutions, such as parallel conductors, higher temperature cables, and improved heat dissipation, should be explored to optimize the design and minimize the number of duct banks required.